My sense is that neither the human brain nor the transformer are the end of history. The purpose of this episode today is to really sound an alarm and say that I think we now have that new architecture. We're going to see more effective agents, more compelling long-term assistants, more compelling long-term AI friends and companions. All of this, if I had to guess, I would say it probably happens several times as fast as the transformer era.
Hello, and welcome to The Cognitive Revolution, where we interview visionary researchers, entrepreneurs, and builders working on the frontier of artificial intelligence. Each week, we'll explore their revolutionary ideas, and together we'll build a picture of how AI technology will transform work, life, and society in the coming years. I'm Nathan Lebenz, joined by my co-host, Eric Torenberg.
One of the most important big questions that I get asked is, what are the chances that somebody invents something better than the transformer? Since 2017, with the introduction of the transformer, attention is all you need. Transformers have dominated the field. One of the big realizations that I had as a relatively recent entrant to the field a couple of years ago from my multimodal perspective at Waymark was, oh my God, it's a transformer solving all of these different problems. As I'm watching art creation come online, as I'm watching language models get dramatically better, as I'm watching all sorts of niche tasks advanced rapidly, image captioning, image matching, video captioning, all these different things, so many things, everything, everywhere, all at once, but all the transformer. So I think I've been pretty clear in recent months on a bunch of different episodes that this is hard to predict. I sometimes call it the $100 trillion question, which is the size of the global economy today. But my sense is that neither the human brain nor the transformer are the end of history. If you watch my AI scouting report, I go through the history of expectations and predictions about how far AI might make it, given raw compute guesses. These date decades back, most notably in the 90s with Kurzweil publishing his Singularity is Near, drawing these exponential curves and saying, hey, right around 2020-ish, 2020, 2025, that's when you're going to have enough compute to match the power of one human. And then later, you're matching all of humanity and becoming truly superhuman. Well, the human level AI has shown up roughly on schedule. It is, as we've covered, in many different ways, human level, but not human-like. In many ways, it is very alien. And yet, this power, which now is in most domains ahead of the average human, and in many domains really closing in on expert performance, this has basically all been driven by the transformer. The attention mechanism is doing everything for us. So I've been really interested in this question. How likely is it that somebody will invent something better than the transformer? And I've been watching out for it. And there have been a few plausible candidates this year, which I've mentioned a number of times. Those include, most notably, RetNet, which is a publication out of Microsoft collaborating with Tsinghua University in China. We also had Lily Yu from Meta on to talk about the megabyte architecture, which was still fundamentally transformer, but a hierarchical approach that was different in meaningful ways. And of course, there's been a ton of improvements, but there have been a few candidates for things that, hey, this might start to look like something that could be even better than a transformer. The purpose of this episode today is to really sound an alarm and say that I think we now have that new architecture. And it is called the Selective State Space Model, aka MAMBA, published in just the last couple of weeks. I saw this paper pretty much as soon as it came out, saw some of the claims, and have gone really deep into not just trying to understand it. That was about the first week since it came out, but then also really begin to project into the future, what is this going to mean? I think if my AI scouting paradigm is good for anything, it should be good for identifying new research that really matters and at least giving a pretty good guess about what that information, what that new research, what that new capability is likely to unlock in practical terms. So that's what I'm going to try to take you through here today. It is going to be hopefully accessible throughout. I always try to use vocabulary words and then the most plain spoken terminology that I can. So I'll try to make it as accessible as possible throughout. It will also definitely be technical. I will be getting into the weeds for sure, deeply. But I actually want to start off with something a little bit different today. So if you'll indulge me, I think it may prove instructive to begin with a little examination of our own human cognition. So what comes to mind when I say the word rainbow? There are a lot of different ways to think about the concept of a rainbow. And I'm sure everybody had a slightly different experience in just those couple seconds that I let you think without further prompting. Some may have conjured up an image immediately. Obviously, we have highly visual thinkers among us. So you may have gone straight to a colorful, vivid image. Others may have gone to smells. I'm not a big smell person, but I do find that the rainbow associated always with after the rain, there's a very distinct smell and a very consistent smell to that. And somehow that is conjured for me very quickly. You can also get a lot more conceptual. Think about it through the lens of, for example, science. What is happening? How is it that light interacting with water in the air is bent differently such that the colors normally perceived as just normal white light are split and we can perceive them individually? You might think of just the history of science as well and what an achievement that was. But you also might think about going deeper into history, thinking about how ancient humans understood the rainbow, thinking about how in various traditions it represents a promise from God, a sense of protection, a sense of rebirth, renewal, obviously associated with spring as well. You might think about just the pure colors. If you're an artist or a creative, or even just a kid who remembers that Roy G. Biv mnemonic, which was never that great of a mnemonic, but that's what we were taught, Roy G. Biv, the colors all in order, how they blend together, how there really is no exact distinction, but it is a spectrum, a sort of continuous space of color, profound in its own way. You might even think of just contemporary identity politics. You might think of the rainbow as a way to express self-love. You might think of the rainbow as a way to make a statement about who should be included in what spaces in society and on what terms. And you probably have personal memories of rainbows as well. Of course, everybody's personal memories will be different. So these are many different lenses on just a very simple concept. And I want to use that experience and all those different lenses to unpack some of the strengths and weaknesses of current AI systems, and also look at how this new AI architecture, the selective state space model, Mamba, state space models more generally, compare not only to the AI that we currently have, but to us. I've done the cognitive tale of the tape in the past, comparing humans to transformers. A lot of what we're going to do here is talk about the humans, transformers, and now state space, and who knows what comes next, future, that I think we can start to get a reasonably decent read on. So let's talk about some of the functions that go into that cognition that we just experienced around the concept of the rainbow. Capabilities that we have and that we take for granted include the ability to accept multimodal inputs. The main ones for a rainbow in particular that we can take in the sight. We can actually see the thing itself. And we can also see the text, which represents the word rainbow. We can hear the word, right? That's how you heard it from me just a moment ago. You heard the word rainbow. And even with touch, you could, if you're a Braille reader, you could have your fingertip interact with an encoding of the language of rainbow and have that rise up to some higher level understanding. So this concept can be loaded in through all these different modalities. Now, I think what's also really interesting is that at a high level, once this concept is loaded into our brains and becomes the focus of our cognition, it doesn't exist in the same way in which it entered. It exists in a higher dimensional, more associative space. All of the different notions that come to mind, that information is not encoded in the word rainbow itself, right? That is just 7 letters in the English language. It's just 7 bytes of information. And yet we can load up such rich understandings. That information is encoded in our brains. It already exists there to be tapped into by this given stimulus. And so we're not just working strictly with tokens. We are working on some higher order concepts, which are not super obvious even today. Like, what exactly is the nature of those concepts and how does our cognition work? Obviously, that's not a fully solved problem, but it is clear that the cycle of accepting a stimulus in, working it up through layers of the neural architecture to the most abstract, the most high level concepts, thinking about it, and then often working back down toward, okay, now what do I want to express, right? That thinking of what happens next seems to happen at this high level beyond words. But then to take action in the world or communicate with others, we have to then translate that down into some lower level thing. That could be motor commands. But for the purposes of today, let's think mostly about generating language, right? And we also generate, from the studies I've seen, just a couple tokens at a time. We have this higher level understanding of what's going on, but our actual words are really rolling off of from our brains into our mouths and into the sound with just a couple tokens of buffer. You can just understand that yourself by just thinking like you just don't know what you're going to say in the future, and where the exact words come from is not super clear or intuitive, right? There is some not fully conscious mechanism by which these high level thoughts that we experience as conscious states get translated into words that can actually be articulated. We also, and this is super critical, this is going to be one of the key concepts to understand for the Mamba architecture and what makes it new and different from its immediate ancestors. But also something that we can do is that we can treat a given input differently depending on its context. Okay, that's super important. So again, we can treat a given input differently depending on its context. So each of those angles that I gave you before, whether it's the mythological or the scientific or the personal memory or a story or a person who loves rainbows, all these different prompts that I can give you, I use that word definitely advisedly, they change the way that you think about rainbow. The rainbow is not loaded in the same way every time. It is loaded in with the awareness of this other information, this other part of the input. And so the high level states that arise as a result are significantly different. And again, you can just understand this through basic examination of your own cognition, I think. Certainly it is pretty obvious to me when I take the moment to reflect on it. And then finally, again, think about this memory, right? I gave short shrift so far to the personal memory. But this is something that, again, we have the ability to somehow reach deep into our own personal history and recall things that we may not have recalled for years, may not have experienced for decades. And so that gives us this sort of long-term individual coherence and identity that is in many ways made up of the fact that we can tap into these long-term memories. So that's human cognition. Okay, contrast now to the current AI paradigm. On the multimodal front, we now have multimodal AIs that can take in all these different kinds of inputs. The most profound ones, I think, are just the ability to integrate vision and language. That's, if nothing else were happening, that would be a huge deal. But there's a lot more besides. We're going to see AIs that have senses that we couldn't dream of having, right? Talk about just seeing additional colors through additional wavelengths, just as kind of one very early example of what that might look like. But there's no reason to think that AIs are not going to be able to take in all sorts of signals that we just don't have either the receptors for or the native ability to parse. And they're going to be able to learn how to take in lots more modalities. This is already well underway with transformers.
Hey, We'll continue our interview in a moment after a word from our sponsors.
Real quick, what's the easiest choice you can make? Taking the window instead of the middle seat, outsourcing business tasks that you absolutely hate. What about selling with Shopify? Shopify is the global commerce platform that helps you sell at every stage of your business. Shopify powers 10% of all e-commerce in the US, and Shopify is the global force behind Allbirds, Rothy's, and Brooklinen, and millions of other entrepreneurs of every size across 175 countries. Whether you're selling security systems or marketing memory modules, Shopify helps you sell everywhere, from their all-in-one e-commerce platform to their in-person POS system. Wherever and whatever you're selling, Shopify's got you covered. I've used it in the past at the companies I've founded, and when we launch merch here at Turpentine, Shopify will be our go-to. Shopify helps turn browsers into buyers with the internet's best converting checkout, up to 36% better compared to other leading commerce platforms. And Shopify helps you sell more with less effort thanks to Shopify Magic, your AI-powered all-star. With Shopify Magic, whip up captivating content that converts from blog posts to product descriptions. Generate instant FAQ answers. Pick the perfect email send time. Plus, Shopify Magic is free for every Shopify seller. Businesses that grow, grow with Shopify. Sign up for a $1 per month trial period at shopify.com/cognitive. Go to shopify.com/cognitive now to grow your business, no matter what stage you're in. Shopify.com/cognitive.
So what about that higher order, more associative form of processing that I described?
It turns out that the transformer is also doing something very similar to the loop that I described of taking in an input, working it up to higher order concepts, and then kind of working it down to make a specific prediction. The transformer is actually doing something very, very similar. It is starting from the embeddings, moving through the layers. And remember, and especially in the big transformers, there are many layers, dozens of layers that successively process the data step by step until finally it reaches the end. And there is a pretty systematic study now of how the different layers work. And it's quite clear, I would say, from a bunch of different research results at this point, that it is in the middle layers that the highest order concepts are the focus of the model's cognition. Just 3 results that I'll mention to kind of ground that, and you can go check into them more. I've covered a couple of these in the recent AI research podcast. One is the influence functions research from Anthropic. They looked at training data and said, how can we tell what training data is most important to a particular output from the model? What they show is that in the small models with relatively few layers, you have apparent stochastic parity, where the things that are most relevant are those that have the same keywords. So you can see that the understanding is relatively shallow. And you can infer that even if the text that is generated passes as correct in some sense, that at least from this analysis, the small models don't seem to have a very sophisticated high-level understanding. But the big models do. When you get up to real scale, and we're talking here like tens of billions of parameters, I think Anthropic was working with something in the sort of 50, 60 billion parameter range. By that time, you see now really sophisticated relationships between the inputs that are determined to matter most and the actual work and the outputs at hand. So that's really interesting, and they specifically locate that in the middle layers. Another concept is editing and changing the fact patterns that the language models have learned. This is a technique. There are a couple different papers on this. One is called Rome, and that one really started to scale up this concept editing work and develop metrics for the robustness of the concept editing, the reliability. And you can do now tens of thousands of concept edits where you, for example, say, Michael Jordan played baseball, right? You want to edit the worldview, the history, as the model understands it so that Michael Jordan played baseball, but you want that to be consistent so that it answers that way regardless of what kinds of questions it is asked. You want it to be robust to simple rephrasings, and you want other things to stay right? You don't just want to replace the concept of basketball wholesale. You still want Larry Bird and LeBron James to have played basketball. And they can do all of those things. by editing concepts within a transformer. And again, that editing is mostly happening at the middle layers. And then most recently, the representation engineering paper, which was from Dan Hendricks and collaborators, where they start to look at the activations, again, in the middle layers, and ask questions about them like, what kinds of concepts can we identify in this information? And indeed, they find that they can both classify and even start to control model behavior with this growing library of high-level concepts, which are represented as a vector direction in activation space in these middle layers of the transformer. So we have pretty good evidence, I think, now to say that when it comes to this aspect of cognition, this loop of taking in this compressed input language, you gradually work your way up through the layers, whether in the human, it's through the visual system or through the auditory system or even through the touch system, and gradually get up to these higher level concepts where you have all these associations, you have all this valence and everything is there. And then after chewing on that for a little bit in a way that we don't have certainly perfect self-awareness of, we can then translate that back down into concrete next token predictions and make language, and transformers are doing something very similar. It is weird, though, that the transformer does that with a homogeneous architecture. You have the embedding at the beginning of the transformer where you convert your inputs into numbers. Then you basically have the same exact block over and over again. And of course, there's a lot of little variations, but the core concept is really the same every time through every layer. That is a multi-headed attention block where the tokens are all computed relationally to each other, and you can figure out what to pay attention to based on the overall inputs. Then you have the multi-layer perceptron, which is dense information processing, but notably that works on a token by token level. Then you also have some nonlinearity, some way of filtering out noisy information. And then you have the skip connections, and you just layer that block over and over and over again till you hit the scale of the model that you're trying to build. And then at the end, you have some de-embedding reduction to specific prediction as well. But the middle is really the same thing over and over again. So I do think that is like remarkably weird that we have created something that doesn't have much specialization of internal architecture. And it's just that the layers themselves end up taking on these different aspects of the cognitive process. There's a division of labor between the layers, even though there's not a difference in form. So I think that's a pretty striking observation.
Turning now to that third point, what about the ability to process the same inputs differently?
This too is something that transformers can do via the attention mechanism. And it is broadly understood to be a very important part of why they work so well. So how does this work? In the abstract, you can imagine two classes of machine learning architecture, two classes of model. One would be where you have the weights, and the weights, again, the weights are the numbers that are learned in the training process, and they are the numbers that are used to transform the inputs through whatever layers or process until outputs are reached. So one traditional, typical, normal AI architecture, machine learning architecture, would just have the weights fixed and just apply the weights in the same way, regardless of what the inputs are. So you feed in some inputs, you convert them to numbers, and then they're just going to be crunched through layer one in a certain way, and they're crunched through layer two in a certain way, and they're crunched through all the layers in a certain way. And that the way that those numbers are crunched can just be the same every time, regardless of what the input is. Most machine learning architectures historically have worked that way. If you go watch the 3 Blue, 1 Brown 2017 Introduction to Neural Networks, which is a classic and has some great visualization. I still recommend that all the time because of just how fundamental and how elegant his explanation is. He does not talk about attention at all. And the types of architectures that he's describing are basically this way. You feed some inputs in, the weights are all there, and the weights just do their thing. Each layer crunches the same way, and that's just how it works. So what's different about the attention block is that inputs have two routes by which they affect the overall process. The inputs are the inputs that get fed in layer to layer through the model, but they also have this other path, the ability to shape what the attention block is going to do. So you may be aware that the attention matrix is different every time depending on the inputs. That's why we have these different, K, Q, and V portions. And first, their nature is determined, and that again depends on the inputs. And then they are crunched against each other. So again, there's two paths by which the inputs affect the number crunching that ultimately happens. They just are the inputs, and then they also affect part of the way the inputs are crunched. That is why the attention matrix is different every time and can't just be totally pre-computed. And this is understood to be a huge reason that the transformers are so powerful. Thinking back again to our experience and the way that we considered the concept of rainbow differently, depending on these compressed supplemental inputs, the different lenses of historical and mythological and scientific and so on, ChatGPT can do the same thing. The transformer, the language models can do the same thing, right? If you say, explain to me a rainbow through the lens of mythology, you will get a totally different answer from if you say through the lens of optics or the lens of childhood or whatever. This is something that the simpler models can't do, right? If you have an image classifier, it may have a rainbow class, but it's just applying the same standard computation to every single image, and hopefully it lands on the rainbow. It's not loading in all these other associations. And this is what this secondary path of influence from the inputs to the computation ultimately allows for. It's a huge reason, and I think this is pretty well established in the literature from a bunch of different angles. It's a huge reason that the attention-based transformer architecture is so powerful. It's that forking path. It's that two ways of the input determining how the information processing happens. It's a big deal because this is what the Mamba architecture unlocks for a totally different class of model. And we're going to get into that in a lot more detail. But before we do, let's talk about the big weakness of the transformer. The big weakness, the information passing that unlocks so much power, is also slow. If transformers are quadratic in nature, is because every additional token has to have a relationship computed with all the tokens that came before it. And that's a fundamentally quadratic computation process. So obviously lots of optimizations and also approximations have been used to try to work around that. And certainly we have scaled context window up a lot. But basically the state of play is that the full, dense, non-approximated attention is still quadratic. And all the approximations largely seem a little worse. Often they can work quite well, but they don't seem to work as well as the full, dense, no compromises attention. So the weakness of attention there is that it's slow, and also that the context window itself, because it is quadratic in the context length, the context windows are fundamentally very limited. Now, we've seen that they have grown a lot, right? And at 100,000 tokens, you can fit the Great Gatsby in. Claude 2.1 is now on the market with up to 200,000 tokens of context. And that is definitely not nothing. It's a lot more than it used to be. Just a couple of years ago, we were talking about 2,000 token windows. And not long before that, BERT, I think, is 512. So there has been definitely rapid growth in the computing power, obviously, that underlies all this. And with that, the ability to extend out these context windows longer and longer. But that's still not that long. 100,000 tokens, that's just one book, right? And if you're reading if you read The Great Gatsby, that is the entirety, basically, of what a transformer can work with at any given time. That also would translate into like a 3-hour podcast. If I take the transcript of this entire thing, it's going to be most of 100,000 tokens. And that's not that much, right? I don't know what my effective token intake rate is per day, but it's a lot higher than that. I hear a lot of audio. I have a lot of conversations. I read a lot of things as well. I obviously have a ton of imagery coming into my cognition. So 100,000 tokens is not much in the grand scheme of things. And for transformers, there is nothing but that context and the weights themselves.
Hey, we'll continue our interview in a moment after a word from our sponsors.
If you're a startup founder or executive running a growing business, you know that as you scale, your systems break down and the cracks start to show. If this resonates with you, there are 3 numbers you need to know: 36,000, 25, and 1. 36,000. That's the number of businesses which have upgraded to NetSuite by Oracle. NetSuite is the #1 cloud financial system, streamline accounting, financial management, inventory, HR, and more. 25. NetSuite turns 25 this year. That's 25 years of helping businesses do more with less, close their books in days, not weeks, and drive down costs. 1, because your business is one of a kind, so you get a customized solution for all your KPIs in one efficient system with one source of truth. Manage risk, get reliable forecasts, and improve margins. Everything you need all in one place. Right now, download NetSuite's popular KPI checklist, designed to give you consistently excellent performance, absolutely free, at netsuite.com/cognitive. That's netsuite.com/cognitive to get your own KPI checklist. netsuite.com/cognitive.
OmniKey uses generative AI to enable you to launch hundreds of thousands of ad iterations that actually work, customized across all platforms with a click of a button. I believe in OmniKey so much that I invested in it, and I recommend you use it too. Use CogRev to get a 10% discount.
You have the weights, they have a ton of information encoded in them, but then they just take their input. They're always waking up, if you will, with total amnesia. And they have a world, to the degree they have a world model, they're waking up with their world model ready to go. But then they're confronting some input that is totally novel, right? And they have no memory of confronting that input before, and they just have to crunch what they're given to crunch. And they can do it in this super richly expressive way because of the forking path and the multiple ways in which the input can ultimately influence the information processing. But at the end of each episode, when the context window runs out, there really isn't anywhere for that to go, right? That information typically is just discarded, and then we come back and we use the LLM-powered assistant again another time with a totally new context. So we've got right now a lot of hacks to try to get around that. This is why we have a system prompt from OpenAI, or custom instructions, as they call it in ChatGPT, because you want to have more consistent behavior. You want to have it sort of know you, but it can't know you. It doesn't have any mechanism to know you. It doesn't have any way to take that context that it crunched in the context of one interaction, one episode, and turn that into any longer term durable memory that it can later use. That mechanism just doesn't exist. So it's fundamentally an episodic technology. And then we have, of course, retrieval, augmented generation, right? The database, or we can save our logs and start to query back into our logs. But from the standpoint of the model, loading those logs in, that's also still just one episode, right? It doesn't have a real memory of that earlier episode. It can only just load in a part of it. And however much it loads in, that's context, right? And you can get into these more elaborate constructions where we save all the logs and then we come through and process them periodically and try to summarize them or synthesize something more useful out of them. That was one of the techniques from the AI Town paper that I thought was most interesting. It wasn't so much just the fact that they had all these guys running around and talking, but they were periodically sweeping through all their recorded memories and synthesizing higher order memories, more compressed representations of what those little bots had experienced, so that later that could be loaded into context more usefully. But again, it's still kind of just a hack, right? Because it's like a language model, which is purely episodic, processing some memories and creating new language, and then that language kind of getting loaded into a model. It's lossy, right? Language, because it's compression, it's also lossy, and it's not necessarily lossy in super principled ways. And this is why the transformer AIs that we have today don't make great companions and don't make great long-term assistants and are not super effective as agents, because 100,000 tokens is not that many tokens if you want to go out and browse the web and do comparison shopping and navigate tricky situations. There's no way for it to learn your preferences, right? To have an instinct and an intuition for your preferences. It's not going to have that. What it can have is explicitly declared preferences at the system prompt or accessible through some database that it can query and load in. But it's never going to really know you. It's never going to have an intuition that is inbuilt to understand you or even just itself, its own history. It's just, there is no mechanism. There's nothing but the context window currently under consideration and the weights themselves. You might say that the memory is missing. I think there are paths, by the way, to fixing this within the transformer architecture. And in an episode a few back where I sketched out the future of the transformer, and so you can go listen to that one if you want the full deep dive on that. That's outside the scope for today. But briefly, we've started to see these additional tokens built into the transformer vocabulary and then into the training process with some pretty interesting results. There has been the backspace token, where with a modification to the loss function, the model can recognize that it's getting out of distribution and add a backspace token and then carry on from where it was before, with still the information that like it knows that it took this step and then encountered the backspace. So it can really help with avoiding going off the rails. That's not yet super commonplace from what I understand, but very interesting result. Another super interesting result is the paper Think Before You Speak. This was the pause token, the thinking token. The idea was that, hey, if we just give it some extra tokens without necessarily having to do anything, but just allow it to crunch a thinking token, train it when it's appropriate to do that, then maybe that can bring about better performance. And sure enough, it does. And so from that, I imagine, geez, maybe a memory token could also make sense. How exactly does that memory token get created is not super clear, but you can start to imagine that you might load in tokens, especially because we've seen this in the multimodal context so often, right? The ability to bridge from one space to another means that you can take an image and convert it into language space. And even with frozen vision model, frozen language model, you can just train a small adapter such that the language model natively knows how to interpret the output of that small adapter, because you've literally transformed image into language space, and to the model, it is understood as language. Even if no vocabulary could get there, you have that ability to shape information into language space so that the language model can work with it. I think there's something very similar to be done with memories, to compress some of the history into maybe just one token. How much memory you can fit into one token, who knows? But clearly, you can fit in a lot more than just one word. We know that from the image work. So exactly what the nature of this memory compression is likely to be is unclear. I can see the beginning of a solution on the transformer mainline AI development path right now, just based on these other kind of behavioral tokens. I can see a memory token also really starting to work. I haven't seen that yet in the research, but I do think it is conceptually possible. But in the meantime, somebody has invented a better way. And this is now bringing us to the real subject of today's episode. So the paper that announces all this is called Mamba, Linear Time Sequence Modeling with Selective State Spaces. This is just two authors, Albert Gu and Tri Dao. You may recognize those names. And it is a real tour force. I mean, what two individuals have done here, I think, has a pretty good chance of rising to the level of that canonical attention is all you need work, which, remember, did not invent the attention mechanism, but in fact, abstracted away a lot of previously complicating detail and demonstrated that the attention mechanism itself, in just this very basic form, was enough to do basically all the tasks that people were trying to do. It turns out it was not all you need for all tasks you might want to do, but it was all you need for the measurements and the ability to examine or characterize a language model that they had available at the time. This is a big deal. Let me first just talk about who the two authors are a little bit. They are both professors. Albert Gu is an assistant professor at Carnegie Mellon. He's also the chief scientist at a company called Cartesia AI. And his Twitter bio simply says, leading the SSM, that is the state space model revolution. The other author is Tri Dao, and he is also an incoming professor at Princeton. He is also a founding chief scientist at an AI startup called Together AI. which has raised $102.5 million Series A. And his expertise is really in performance. Super close to the metal, highly optimized algorithms for really making the most of your GPUs. If you know his name, TreeDAO, you probably know it from Flash Attention. And Flash Attention was a major advance in how attention could be computed without any sort of approximations, really doing the full computation, but doing it in a way that worked much better, just based on how the data is shuffled around and what moves to different parts of the overall GPU physical hardware. Finding a better way to do that made it just dramatically more efficient and has been a huge unlock and just major compute savings. So these are the two guys. It's the leader of the state space model revolution, and it's a really accomplished hardware expert. And that's Albert Gu and TreeDAO.
So what's the big difference here? It all starts with the concept of the state.
The thing about state space models that is so different from what we have now come to understand as a norm in the transformer is that it has an internal state, a state that evolves through time and also propagates through time. Okay, so one way to think about it is that it is something that outlasts the single interaction between the weights and an input. So if a transformer has all these weights and it takes an input and they interact, and yes, there's that fork, but there's not really anything else, right? What the state space model adds to this at a conceptual level is the idea that, okay, yes, you have your weights and you have your input, but you also have an internal state. And the nature of the calculation now becomes, I'm going to process both the last state and the new input by the weights to get not just an output, yes, an output, but not just an output, also a new updated state. And so this state becomes a long-lived thing that can go on and on through time. With all this motivation, it should appeal to you as something that's like, this state can go through step after step and it propagates through time. It's not the output, but it is a modified state that is used to calculate the output at each step. Like immediately, I think, it sounds like there might be something there that could help solve the memory problem. And indeed, these state space models, they have some real strengths. People have been working on this for the last couple of years. There have been a whole bunch of papers about it, a bunch of results. It does have real strength when it comes to extended memory. There are specific benchmarks that try to test this, where you have long strings, and these often have been historically programmatically generated. And they're tasks like, here's some sort of expression, which may have tons of parentheses in it and brackets and curly brackets. Code is like this. In arithmetic, you can just write out infinite arithmetic with whatever sort of open bracket, open parenthesis notation. And then in coding, you have to close those things, right? So the challenge then becomes for the AI, can I give you this giant long sequence of all of this stuff with all these order of operations, open parentheses, open square brackets, and can you close it? Can you close that in an effective way? The state space models have dominated this category. This is one of the few things where the transformer is not supreme. And the big reason is that these things can get arbitrarily long. And it's really hard for the transformer to keep up with these arbitrarily long things. Like some of them just can't do it. There's literally no way. So the state space models have already shown, even prior to this state space moment, that there is a role for them, that they do have some really desirable memory properties that the transformer does not have.
Now, how this works is actually pretty complicated, but also principled. I followed references back to an earlier Albert Gu and TreeDAO collaboration, in that case with other authors as well. And the original HIPPO paper, HIPPO, H-I-P-P-O it's called, describes how long sequences can be compressed into really small state representations using a process of projection onto a basis of polynomial functions. Now, that's complicated math, but the way they evaluate memory back in this original paper is for its ability to memorize an arbitrary, noisy input sequence. And there are different ways of doing it where you weight more recent data more heavily or weight all data the same. But what they show is that you can create a slightly lossy, yes, but still extremely useful representation of a sequence extremely efficiently by representing them in this way.
And by the way, they have some pretty nice scaling properties too. So there's motivation to work on this because the structure of the computation is actually in many ways a lot more favorable than the transformer. Each inference step takes the same amount of time, constant time inference. Why is it constant time? Because you have a state and the state is of a fixed size. Okay, that's important. The state is of a fixed size. It changes through time, but it doesn't grow through time. So the state, because it's of a fixed size and a new token of input, those two can be considered the inputs. They are processed by the weights. An output token is generated and the next state is also generated. And that takes the same amount of time, regardless of how long the sequence historically has been, because the state itself doesn't grow. That's in contrast to transformers, where as the context grows, you have this quadratic nature of the computation. There are caching strategies that help. You're just able to cache the parts that you already did, so you don't have to redo it with every single token. But fundamentally, you still have that quadratic calculation. The state space model, though, it's constant time inference because the state itself does not grow. It evolves, it changes from step to step, but it does not grow. So constant time inference, that's great. And then that also means linear scaling with the sequence length for the purposes of training. So this is awesome, right? Like this is much better. If each step takes the same amount of time, then you're in a fundamentally different regime than if each step is starting to take a little bit longer than the last step. Huge difference. Okay, so what's the problem? Well, historically, the problem is they just don't work as well. You've got these few areas, these kind of oddball parentheses closing tasks that the state space models do really well on. But for most language modeling tasks, that is to say, like all the stuff that ChatGPT can do for us that we find so much value in the transformers for, the state space models just haven't been as good. Interestingly, I think that the authors of this paper do really give you a pretty good sense for their motivations for this work in conceptual terms. It's not as accessible as what I'm presenting here. But this is such a tour de force because it begins with such high level conceptual insight. And then they go, so deep all the way down to this super low level code, which is, by the way, open source, to actually make the implementation of it work. But just starting at the very high level, they're like, all these state space models that we've been using so far have been of the simpler class where the actual layer by layer transformations are fixed and the information just flows through it. They don't have that property like the transformer has and like the brain obviously has, where the nature of the computation, that is, by what numbers will the inputs be transformed, the state space models have not had that ability to do that dynamically. So that really limits what is sometimes called expressivity, just how rich, dynamic, powerful can they be. Their motivating observation is that the state space models have probably been limited by that they can't match the transformer because they just don't have the same multipath means for the inputs to affect the information processing that unlocks the power in the transformer. So you might wonder, well, why is that? Why were they designed that way? And historically, as I understand it, the reason has been that was the only way to make the mission feasible, with reasonable resources and time. The math of this can get pretty abstract in terms of the notation, but basically the state space models that have come before have been designed so that they can be represented and computed in parallel, and also so that they can be represented and computed in a recurrent fashion. The parallel form is called the convolution, and that's less important for non-technical folks than the idea that there is a way with the traditional state space models to do the calculation that is highly parallelizable. And that's obviously super desirable. The transformer is also highly parallelizable, which is a big part of why it's been able to scale with GPU infrastructure. So the state space models, people want to do the same thing. Can we make this highly parallelizable so that we can hopefully scale it? And yes, you need to have the convolutional form, and then you can do this calculation in a highly parallelized way. And that's, by the way, used mostly for training, because you have these like large established batches of what the text is. You want to process that in batch. You don't want to have to do literally just one token at a time. That's pretty annoying. So you have to have this convolutional form, which allows for this high level of parallelization. But then when you switch to inference, then it does become a recurrent process. Inference, next token prediction, you're just predicting one token at a time. This is called auto-regressing, where you're taking your token, feeding it back in as input and running the same process over and over again. The loop is feeding the output right back into itself as input, but it is still only just doing one token at a time. And you really can't parallelize beyond that. So you'll see the training, and also if there's a long prompt, then the initial mode could be convolutional in structure and parallel in computation. So that can happen quickly. And then when you're actually like generating new stuff, you have to go one token at a time anyway. So that's the recurrent form. So all these state space models had this dual nature. They wanted to have the parallelizability, but then of course at runtime, you're going to generate one token at a time. So here's the key dual breakthrough for the Mamba paper. They said, okay, is there any way that we can broaden what a state space model can be so that the calculation that is done is influenced by the inputs in kind of a similar way to what the transformer does? We want the inputs not just to flow down a assembly line, so to speak, where they get, transformed by exactly the same numeric machinery each time, but we want the nature of the transformations as we go down the line to also depend on what the inputs happen to be. How can we make that possible? Keep in mind, these state space models are a little bit different. You have the state as it currently exists, and then you have a new input, and then those get processed by some parameters such that an output gets generated and also a new state. You can look at the diagram in the paper. But ultimately, if you are just generating content with this, then you're again feeding each output back in as input, but you're also feeding the new state in as input. And the old state, you can let go of, right? It just goes away. Like the state has evolved, the state has changed. So what they decided to do is say, okay, what if we let all these parameters and what if we let the transformations that we're going to do to the state and the input depend on the input itself? That's like, on some level, a conceptually simple thing to do. This is like a relatively small change in the equations that define the architecture. But the key problem with it is that now you truly can no longer have a convolutional form. And so the computation is no longer in the way that it was. So you're now really constrained to the recurrent form. And so you might think, well, geez, that's just like not going to ever work. We have to be able to parallelize in order to really make this scalable. And this is where TreeDAO, one of the leading experts in the development of these super efficient low-level algorithms, comes in. So what they do here is they call hardware-aware algorithm design. Parts of it will be beyond the scope, but I want to at least take a little bit of a dive into this to give you some intuition for what it is. And then there's plenty of room for greater depth of study beyond this as well. The hardware that they use is the NVIDIA A100. And that is a state-of-the-art machine until recently. It's been superseded now by the H100, but the A100 is no slouch. It's just one generation behind the latest H100, and it's been the standard, it's what GPT-4 was trained on, for instance. So it's a big machine. It costs thousands of dollars. It runs at 400 watts, which is not nothing. That's still only half an electric teapot when it's boiling your water, but it's like 20 light bulbs in today's world. So it's not nothing, but it's also not like a huge machine. Thousands of dollars, 20 light bulbs worth of energy. And what they really try to do is figure out, how can we organize this computation so that it can work fast on this machine? Knowing all the specs and knowing that we have a world-class expert in TreeDAO in terms of writing the CUDA code that is going to manage how this information moves around in a very strategic and ultimately effective way. What they do is, first of all, they look at the nature of the chip. And they note that there are two kinds of memory that are available on the GPU. And this might even be a little bit of a simplification, because there could be some even in between from diagrams I've looked at. But the two that they really call out are the SRAM, which is also called the SM, or the shared memory. And then they have the HBM, which is the high bandwidth memory. And these are two different kinds of memory that serve very different purposes, actually. On the A100, there are 6,912 CUDA cores. Those are the actual processing unit that do the math, right? That do the multiplication and addition, that ultimately constitutes the matrix multiplication, that ultimately constitutes all this stuff. There's 6,912 of those on a single A100 chip. The shared memory, or the SRAM, this is the memory that is absolutely closest to those cores, where the actual number crunching takes place at the very lowest level. There is this SRAM shared memory right next to that, highly integrated with it, and amazingly, not that much of it. The amount of SRAM on an A100 is just 164 kilobytes. 164 kilobytes. That is, with one letter being a byte, that's actually less than the context window on the leading LLMs. But that is the memory, limited as it is, that the cores communicate with most directly. And that's the absolute fastest access memory that they have. The next level of memory out, the high bandwidth memory, that is the much bigger memory pool. On the A100, it's 40 gigabytes of memory. Okay, so that's obviously qualitatively different, like 5 orders of magnitude-ish greater. So totally qualitatively different thing. This is where the parameters get stored, right? When you have these giant models, however many billion parameters you're talking about, you multiply that by a sort of integer factor. It depends on the quantization, like how big the numbers are in terms of how many decimal points they have. But basically, if you think of a number as a couple of bytes, how many billion parameters and that's going to tell you how many gigabytes of space it's going to take up. So a 40 gigabyte A100, actually not even enough to run. That wouldn't be enough to store the entirety of GPT-3 weights. 175 billion parameters is going to be bigger than 40 gigabytes of memory. So then you start to get into arrays. And again, there's a lot of intelligence to how do those parameters get loaded in? How do they move? We don't want to be waiting on them. There are bottlenecks everywhere in this process. So you've got the cores where the actual number crunching happens. You've got the SRAM, which is the memory that is small, that is most closely integrated with that. And then you've got the high bandwidth memory outside. That's where the parameters are. You're going back to flash attention. The advance there was figuring out how to better manage the movement of the parameters from the high bandwidth memory into the SRAM and back, and exactly what order that movement and that calculation should be done to really get the most from the hardware. The naive interpretation, it turns out, way less good than flash attention. And you really have to understand the design of the chips. You really have to understand CUDA at a deep level to be able to write this level of optimized code. And Treedao, how many people in the world can do it, but he is one, and certainly one of the best. Okay. So what is the hardware aware algorithm as it exists today? Well, the big thing seems to be that the model state, never comes off of the SRAM. It is only dealt with in that highest speed, closest to the core memory. So the parameters of the model, those will sit in your high bandwidth memory. The inputs can then be used to interact with those parameters so that they are different each time, right? So that it's not just this super consistent assembly line type of thing, but where the individual stations or the layers as you go down that assembly line actually do different things depending on the input. That process inevitably, because there's a lot of parameters, involves accessing those parameters on the high bandwidth memory. But the state itself, this thing that propagates from one inference step to the next, holding its size constant, right? Evolving its value, evolving its content, evolving what information it contains, but holding its size content, that stays within the SRAM all the time and is not, unless you intervene and say, okay, we want to extract this information, it's never exported off of the SRAM from state to state at all. And that seems to be the big unlock that allows the Mamba architecture specifically to run fast. Okay, so this hardware-aware algorithm, this hardware-aware management of the state is super key and it's super technical. Without it, if you had just a naive implementation, this thing would be too slow to run. It would not be effective, would not be scalable because it just can't run fast enough. So again, the code for this is all open source. They have a repository out there. I am not a CUDA code expert by any means. I did copy some of it into ChatGPT and start to orient myself to it a little bit that way, but it's out there. And it's super, super detailed, hyper-optimized code, super, super technical. The core idea, again, just keeping the states on the SRAM so that doesn't have to come on and off all the time, using up the bandwidth between the high bandwidth memory and the SRAM. To give you just a little bit of a sense of additional techniques, they highlight a few. One called kernel fusion, which is basically when you have multiple different transformations, depending on the nature of the linear algebra and how the transformations relate to each other. Instead of taking an input, multiplying by matrix A, then getting the result, then multiplying by matrix B, you can often reorder the computation. So you do the matrix A and B interaction first, and then you have one net thing that you can apply to each of the inputs, right? That's obviously highly simplified, but that kernel fusion concept is taking multiple transformations and collapsing them into a single transformation. That can only happen under certain conditions. It can be really complicated to do. But again, if you want to maximize the performance, then this is like a pretty core and well-established technique. Another big one that they do is called recomputation. So this is in training because you're trying to minimize the traffic between the high bandwidth memory and the SRAM to make things as fast as they can be. You don't really have the ability to save all of the activations or save all of the gradients along the way. So they use a different technique, which is called recomputation, where they basically compute the activations and the gradients as they do the backpropagation step, which again takes more compute, but less moving of data around. And it turns out that the moving of data around is the more pressing bottleneck. So actually recomputing certain things in these instances can be much faster. You want more on that? You're going to have to dig in yourself and get deeper. But zooming out again, the upshot is with a hardware-aware algorithm, they've made such a dramatic performance improvement on the way that state space model calculations can be performed that they're able to support this greater generalization, this multiple paths for the inputs to impact the nature of the information processing, much more transformer-like. Also, again, human brain is clearly doing something like this. They're able to support that despite the fact that it means no convolutional form can exist and therefore your parallelization is greatly limited. They're able to support that because of this super hardware-aware, super sophisticated, low-level algorithm design. And with that all sorted out, it actually allows them to begin to scale. So they have trained a bunch of different models, a couple of different modalities. And for language modeling, they're doing this on a couple relatively small models, a 1.5 billion parameter model and a 3 billion parameter model. And they go up to 300 billion tokens trained. That's a pretty decent number. It's a long way from state of the art. GPT-4 was generally thought to be trained to like 10 trillion tokens, which would be 30 times the 300 billion that they did here. Llama 2 was trained to like 2 trillion tokens. So this is also still like an order of magnitude lower than the Llama models, even the small ones. But it's also like not trivial, right? To train up to 300 billion tokens, that shows that there is some scalability, but it also gets you far enough down the loss curve that you can start to get a decent sense for, okay, just how good is this thing? And this has been the thing that made the headlines, right? These are the curves now that we can say, this seems like a really big deal because they are beating transformers on language modeling. To say that's a big deal would be definitely an understatement, right? Again, going back to the very beginning, one of the most common, super big, super high impact questions that I'm asked is, are we going to see something better than the transformer? And here we are seeing something that is marginally better than the transformer. They look at this in terms of flops, training different architectures with the same number of flops and comparing the loss curve. They show that basically, if you have a short sequence length, the Mamba architecture just slightly seems to outperform the best transformer version that they use. And again, one of the authors here is somebody who created flash attention, so they should have a pretty authoritative take. If you had a naive implementation of any of these things, you could cook the books. But they have a vanilla transformer in this paper, and then also a transformer plus plus, which they describe as the best transformer training recipe that they know. And basically the Mamba on the 2000 token sequence length just basically exactly matches it. And then they look a little beyond that, now start to look at an 8,000 plus token sequence length. And you can see there's like actually a little space now between the Mamba and the transformer, where the Mamba is lower, it has lower loss, lower perplexity. So this is right off the bat a big deal, right? This is like, wow, on these core measurements of just broad pre-training, as far as it's been scaled so far, and this is out to like 10 to the 20 flops, they are beating the transformer. This is like still 5 orders of magnitude from GPT-4 in terms of flops. But if you've studied the scaling laws, you know that one of the big findings over the last couple of years that has guided so much of where the big investments have gone has been this observation that scaling laws do kind of work. I would say that there is a lot more scaling to be done, obviously, from 300 billion tokens to 10 trillion and beyond. There's a lot more parameters that you may want to have in the model eventually over time. There's a lot more to be explored in really all different dimensions of this. Like, you can't predict the exact behavior of an AI based on pure flops, but with a reasonably high level of confidence, you can predict the aggregate loss. Those curves are actually pretty smooth and pretty predictable. So if you see something that is beating the best architecture, even in a somewhat low flop regime, and you can see that it holds from 10 to the 18, 10 to the 19, into the 10 to the 20 flop range, then you have a pretty good chance that it's going to extend into higher orders of magnitude as well. Given how solid scaling laws have been and how these curves look, where they have a very similar shape, it seems to me quite likely that we will again see a pretty predictable scaling law that can be developed for the state space models as well, and that it probably will carry on a few more orders of magnitude. They also do, and I won't get into this in too much detail, but they also do other modalities in the paper. The one that I think is the most interesting is DNA, because naturally there are long sequences. Why am I harping on sequence length? Just as a reminder, because this whole thing is about solving memory, right? So you can compare 2000 sequence to the transformer 2000 sequence, but the transformer does well at 2000 sequence. You can do that again at 8. And these days, the transformer does well at 8. But the transformer can't go, to 1,000,000 very easily. So why did they not test language on longer sequences? My guess is because there aren't super readily available longer sequences of language just ready to go for training. This is something that perhaps they could clear up for us a little bit. But then they did go on to do training with super long sequences on DNA, up to 1,000,000 tokens. And what is so striking about their result with the 1,000,000 tokens on DNA is that they don't see performance loss even as they go up to 1,000,000 tokens. And basically no other architecture has that quality. Every other architecture that they study, as the sequence length gets longer, they see a significant drop in performance. But with the Mamba architecture, even up to 1,000,000 tokens, they see improving performance. This is a huge deal, right? Again, the whole point of this, or the whole motivation, the whole reason I think this is such a game changer, is because I think this unlocks the ability for models to start to develop longer term memory. And I think a lot will flow from that too, 1 million tokens is a lot, right? It's 5 times longer than the state-of-the-art transformer. And this is just the very first paper on the Mamba architecture. So there's some other stuff in there as well. They work on audio. They have some kind of toy problems that are interesting to look at that kind of show how the previous state space models just couldn't do certain things at all. But the new design that they have does work. And this is where they also, by the way, introduced the concept of selectivity. The state space models in the past were what the authors call linear time invariant, which is a fancy way of saying that the inputs proceed down an assembly line and they get transformed in exactly the same way, regardless of what they are. Whereas in contrast to that, the new thing with the selectivity mechanism that they introduce, that's where you now have different transformations happening as the data gets processed, again, depending on the input, all within a single inference step. So key points, it's beating the transformer on these kind of familiar comparisons where you can say, hey, what does it do at 2000 sequence and what does it do at 8000? And let's take that up to at least 10 to the 20 flops. And then they're also seeing these really remarkable demonstrations on both the toy problems and on these DNA tasks, where the longer the sequence gets, the more the model improves. I think that's just a really, really interesting phenomenon from which we can start to see through the fog a little bit and hopefully figure things out. One other really interesting aspect of all this is the inference throughput on the A100. They show that the batch size that you use influences tremendously how much throughput you get. The GPU is built for extreme parallelization. If you're just running one autoregressive sequence through an A100 80 gigabyte chip, you are not getting the max out of it. And that's true across any of these architectures because it can parallelize more than just a single autoregressive unrolling can parallelize. So they show that with their Mamba 1.4 billion parameters, that you can just run a bunch of individual autoregression inference processes at the same time. And it looks like an A100 can handle essentially 64 concurrent inferences really without any trouble. And that's where it seems to max out its parallelization. But these are all better than the transformer. It's all higher throughput than a transformer of similar size. So a big deal. Now, again, the transformer, a little bit more parallelizable. You can have a bigger transformer that sits on multiple different devices. And it's not clear exactly how that's going to work as people try to scale up Mamba, right? Because you have this state and it's in the SRAM and you're minimizing this input and output. So I think there's definitely more work to do there on like exactly how it might scale beyond, say, 7 billion parameters. But 7 billion parameters is already quite a lot. A lot of models are working at that scale and doing important things. And the throughput is just much, much higher on this single A100 with the Mamba architecture as compared to the transformer. We've got a lot going for us here, right? We've got something that is demonstrated even before this work to have much better long-term memory properties, but just wasn't generally powerful enough to be competitive with transformers. Now we've got a conceptual generalization of the state space model that puts it into transformer territory and perhaps even a little bit better on these core language modeling tasks. Huge deal. It does come at this cost of not being as parallelizable. You have to do it in recurrent form, but hardware-aware algorithm design makes this feasible in a way where it is actually faster than the transformer, at least up to the scale of the devices that we have. And it's again demonstrated that the longer sequences, the better it works. With DNA, we're talking up to 1 million. With these toy problems, again, up to 1 million tokens. That is a big, big deal. And there's one more thing in the paper that I think is interesting as well. They also try just your very first thing in terms of integrating the state space model and the attention model. What does that look like? They basically show that if they interweave the Mamba and the multi-headed attention architecture together, then it further improves the performance a little bit. Not that much, but it does in fact improve the performance. And you can just see clearly that the loss curve is just a bit lower. And they say the Mamba multi-headed attention architecture is only slightly better, which to me is like, okay, yeah, maybe it wasn't that much better, but like it is visibly better. The loss curve is lower, and you've only tried one basic interweaving approach, and already it was better. So I think there's a lot more where that came from. Okay, so what else do we know, right? Well, the paper was published. There's also the code repository that is published. There's also the model that is published that is trained up to the 300 billion tokens. Your 2.8 billion parameter model is something like 6 gigabytes. And now people are starting to work on it. So an obvious question would be, what other techniques that kind of already exist work with this model? Interesting data point on that is that there have been already a couple of people who have gone out and fine-tuned it. One that I've spent the most time with is a project called Mamba Chat. Haven HQ is the company behind this. Haven is all about helping you fine-tune models for specialized tasks. Justice Mattern is the individual. So they dive into this and basically take a pretty simple approach to doing the fine-tuning. It seems like the core libraries there mostly work with a fine-tune on 16,000 chats out of a data set called Ultra Chat 200K. You get a Mamba Chat model, and in your browser, in a Google Colab notebook, you can run this Mamba Chat. So I've spent a little bit of time doing that, sitting and just looking at the performance of the Mamba Chat. Basically, the chat works, and it can chat with you very normally. It seems to know stuff. It can be induced to hallucinate. It summarized very effectively for me at 500 tokens, no problem. At 1,500 tokens, no problem. At about 3,000 tokens, it seemed to lose coherence. And I was quite interested in, well, if this thing is built for long-term memory, why doesn't it seem to handle long sequences well in text? And basically what I came to in trying this and in reading all the papers is that it hasn't been trained on long-term text. The magic of the state space model, which we do see demonstrated in these other modalities, like the DNA and the toy problems, is that it can carry information forward via the state indefinitely. But that doesn't mean it will. And in fact, the average length of chat in this Ultra Chat paper is 1,467 tokens, so under 1,500 tokens. That is super small, right, compared to today's even just context windows. We do see that the model is able to go beyond that length, but not like dramatically beyond that length. And I think if there's one thing that should keep us all grounded, this is the thing that is least well proven as of now, and where there is a little bit of a leap required. So that is definitely worth keeping in mind as a possible reason that some of my downstream inferences and speculations may not actually work. My experience also in terms of using this on Colab was that it was like sometimes fast, sometimes slow. I wasn't able to get an A100, which is the hardware is used in the development. Instead, what Google Colab gave me, even with my paid account, was a V100. That is one generation before the A100. So it's not like a slouchy machine, but it's not on par with the A100 either. So not exactly sure how to interpret the speed. Sometimes it seemed quite fast, and other times it seemed quite slow. Just for like objective comparison, the V100 has 96 kilobytes of shared memory as compared to the A100's 164 kilobytes. So it's a little more than half. In any event, it is clear that the recurrence is a fundamental limitation on like just how fast this thing can work. And even from the paper, with a single A100, they expect that you will get 58 tokens per second if you're just running a single line of inference. 58 tokens per second is faster than you can read. So it's fine. We speak at 150 words per minute. Most people can read a couple hundred words a minute. Speed reading, you get into 300, 400, 500, 600 words a minute. So it's comfortably faster than you can read with the 7 billion parameter scale. If you imagine a 20 billion parameter scale, it's not exactly clear how much that will slow down, but let's just say you get down to 20 tokens a second. Now, maybe you're actually kind of waiting for it as an individual user. And certainly if you're doing like background processing, the latency does start to become a factor. At Waymark, for example, when we generate a video script for somebody, we may be generating 1,000 tokens. And this might be the kind of thing that could take the better part of a minute. So it isn't trivial. The latency is still an issue. even with this like hardware aware design. And I wasn't fully able to characterize that in my own experimentation on Colab. But fine tuning basically works. The libraries, the data sets, the ability to like get it to be a chat assistant, really no obvious problem there. Summarization seemed to be limited by not having been trained on super long context, and speed was hard to assess. But again, I want to zoom out a little bit and just consider the fact that maybe these head-to-head comparisons are kind of missing the point, or at a minimum, they're just scratching the surface of what we should be thinking about. Because the way these results are reported is that, okay, this Mamba architecture outperforms the transformer when we train it on 2000 or 8000 sequence. And again, the 8000 is more outperformance than the 2000, which is almost indistinguishable. So as we go to long context, we are seeing advantage, but these are pretty standard transformer measurements. And you're not necessarily playing to the Mamba architecture's strengths. If the whole point of this is that it can have long-term memory in a way that the transformer just can't, because it has this state that is long-lived going through time, I would just emphasize that none of the tests are really meant to test that. All of these benchmarks are things that like transformers can do. None of them really are things that are fundamentally different from what the transformer can do. And so there may be whole areas where this Mamba architecture, especially as you start to think about long-term memory, there are probably all sorts of things that the Mamba architecture can do that the transformer just can't do at all. And this is where I want to start to get into somewhat more speculative scouting work, but hopefully you'll agree pretty well grounded and likely enough, I think, to happen that this is something we should start to take seriously and plan for. What can we do with this state space architecture that is now as expressive, as powerful at the unit level as the attention-powered transformer, but which has potentially a lot of different surprises and nuances and idiosyncrasies left to be discovered? Remember just how many things we have seen that are just plain weird about the transformer AIs. I suspect that we may see similar amounts of surprises from state space models. But it seems quite clear that we can take this architecture and start to think about breaking out of context windows, that we can think about new training strategies that are designed, engineered data sets that are designed to encourage long-term coherence, to encourage adversarial robustness, to make the model behavior more predictable, because you have this ability now with the state to encode long-term context. We've really only barely scratched the surface of that kind of data set creation. Again, the chats used to do the fine-tuning, 1,400 tokens. That's nothing. That's a handful of back and forths total, right? A book, The Great Gatsby, is almost 100,000 tokens. That's nothing in the scheme of what a human processes. These architectures have been demonstrated up to 1 million, but the loss curves were still going down at 1 million, right? There's a pretty good prospect, I think, that we could start to think of millions, maybe even tens of millions. And then again, I think maybe all of this is missing the point if we try to frame it as state space models versus transformer. Is Mamba the transformer killer? The answer there is almost certainly no. These different architectures, as I hope now is starting to become more intuitive, they are fundamentally different things. They do things in fundamentally different ways. And from that, it seems very likely that they will have fundamentally different strengths and weaknesses. And all of this analysis so far is largely conducted on what you might think of as the transformer's home turf, right? It's all on short sequences. It's all on familiar benchmarks. And these are the things that we test because these are the things where transformers have traction. We don't go to these super long sequence things because the transformers don't really work on them. We don't even really have the data sets. There are a couple, but there are not all that many. So when you see that the Mamba architecture is outperforming the corresponding transformer almost across the board on all these benchmarks that are fairly standard in the field, then I think you have to also keep in mind that we're not yet even really playing to this new architecture's strength. There is, as we broaden our thinking about how we might use this thing, we are likely to see that there are areas where its performance, its outperformance is even bigger. And we might also see, by the way, some areas where its performance is inherently less. So in challenging myself to, well, what is probably worse about this state space model paradigm compared to the transformer? I think the most fundamental thing is that the state carries all the information from the context or the episode into each inference step. If important information was let go in a previous inference step, then it will no longer be available in the state for the next inference step. So that's a pretty important one, right? It's like you have a long-term memory, but once you let go of something, it's gone. That's going to create some pretty different dynamics, I suspect. I would guess that a state space model, for example, might be more likely to just simply miss some things or appear blind to certain details. And attention mechanisms are not always great at this either, but because they do compute every token in relation to every other token, if you are looking for like a diamond in the rough, right? If you load in the Great Gatsby into Claude and you put one weird sentence in there and you say, spot the weird sentence, at a minimum, you can say that the attention mechanism is computing the relationship between those tokens and all the other tokens. And it's likely to pop something up weird when it does that, such that it can probably identify the right thing. I don't think that comes for free. I think they train on that stuff. They train on increasingly long sequences to create that long-term coherence in the transformer. But you do have that every token to every token. So to spot a diamond in the rough, you have the opportunity to make sure you are looking at every token as the challenge arises. In contrast, if you're using a state space model and you've processed a bunch of information, gone through a bunch of history, and at each step along the way, the state is evolving, and that means incorporating new information and encoding it into the compressed form that is the state, but it also means letting go of information over time. Then once it's gone, you may not be able to say, oh, hey, sometime back in this episode or in this context, there was something weird. Can you now tell me what's weird? It may have just identified that as an anomaly at the time and let it go, such that you may not be able to retrieve that. So I'm starting to get a little bit speculative here, but I think this brings us to the question of what's next. And I think there are two big things that are really going to be next. There is going to be the sculpting of memory, and there is also going to be the remixing and the recombining of architectures. And again, remember, even in the Mamba paper, the Mamba interwoven with multi-headed attention is the best performing version. The Mamba version beats the vanilla transformer, but the hybrid already beats the Mamba. And again, this is the attention is all you need paper for the selective state space model, right? This is the one where they're saying, hey, look, we have a new thing here that is as powerful and is in fact beating the transformer on its home turf, right? On all the familiar benchmarks that you know and love transformers for. The new thing is beating the transformer on that stuff. And then, hey, look, if we just do the most naive recombination of the two, it works a little bit better yet. Now, to me, that suggests that we're going to see a lot of remixing. So let's talk about sculpting memory and remixing. Sculpting memory. First and foremost, this is going to be a data question, I think. More than ever before, we are going to need intentionally designed training data. We are going to have to be really careful and thoughtful about putting together long sequences and what we want models to learn from those sequences, what we want to encourage them to retain, what we want to encourage them to let go of. And this kind of work, this data creation work, is a slog. It definitely can be resource intensive. It can be a grind. And it's not always considered super glamorous, but I think that it actually may be the most important work that is going to be needed to unlock the power of the state space models and the long-term memory function. Because at least from this fine-tuning that we've seen, it's not happening automatically, right? If you just go train it on short sequences, does it handle long sequences? It seems that not by default. And that shouldn't really shock you, right? If you are optimizing something and you only ever optimize for retaining information for a certain length, then what happens when you give it a ton more information? It may kind of gum up the works, right? When you see these models going off the rails, it's not exactly clear what's happening there. Certainly, there's a lot more work to be done to understand the internals of these models. You might think that like the state is getting clogged up with like too much information and it's just becoming too overloaded and not working well. Maybe it's not letting go of things as it should. You can also imagine having the other problem, as I already sketched out, where maybe in certain situations it has let go of things that you wish it didn't. So we're going to have to create data sets with, I think, a high level of intention to really shape how we want the memory to work. If we want to have needle in a haystack type behavior, we can probably incentivize that quite directly, even with synthetic data, right? To create situations where there's an anomaly and you need to be able to identify the anomaly much later on. That would really incentivize a certain kind of information retention that is like anything that is kind of contrastive or out of step with the current state is super important, must be maintained. On the other side, again, you could train in such a way where if that never comes up in the training data, if that diamond in the rough type thing never comes up, then it probably won't happen by default, right? The state will not retain that information if it is not incentivized to retain that information in the training process. And the training process largely is defined by the data that it is learning from. So how do you want to shape, if you wanted to do some of this data work, you could think to yourself, how do I want to shape the way that AI long-term memory is ultimately going to work? What behaviors do we want it to have? What qualities do we want it to have? Let's start to think about data sets that can teach those qualities and behaviors. Again, I think this may prove to be the most enduring because everything else that's going to happen is going to remix, but the data sets actually seem to last longer than almost anything else. Certainly MMLU, the math benchmark, these are one of the few things in machine learning right now that's like 3 years old, but continues to be state-of-the-art relevance. I think there is something similar to be done in terms of data set building for the state space architecture era. By the way, a lot of that probably private. When you think about long episodes and you think about how much investment companies make in training their people and how long that process is, how many tokens are represented in an employee onboarding and training process, it's a lot. So you would expect, I think, that private companies would be well positioned to create a lot of this data. So that's data. The data, I think, is going to prove to be super important. Architectures. Again, I think when people ask, is this the end of transformers? Or is it now like Mamba or state spaces are all we need? I think that is kind of the wrong framing on the question. The way I see this unlock is we used to have one mechanism that is the attention block that was so powerful, so much better at almost all tasks than almost everything else, that we literally just used it and only it, right? Even knowing that, hey, we see that these layers are doing different things, right? Going back to taking in a stimulus and working it up to higher order concepts and processing it in the middle layers before then working your way back down to a tangible next prediction. That's all done by the same thing, right? It's kind of crazy. Now we have the existence proof that, okay, with a state space model, you can achieve similar, even slightly better power, the Transformer's own home turf tests, flop for flop parity, better scaling properties, faster, more throughput. Amazing. But I think the real way to think about it is that we now have these two blocks, these two units, and that they each have different strengths and weaknesses. And the real question is going to be, how do we combine them? And we are starting to see some developments from just the last couple of weeks where this kind of thing is starting to happen. So one, from Together, which is the company where Tree DAO is one of the co-founders and the chief scientist, we have this new model called Striped Hyena 7B. And this is a combination architecture of, on the one hand, the attention mechanism, and on the other hand, the state space model. This is not yet, from what I can tell, and I don't believe they've published a full paper on this. This seems to be a more commercial release, this Striped Hyena 7B. But they describe it as offering a glimpse into a world beyond transformers. It is notably not a world beyond attention, but it is a hybrid structure that includes a state space model. As I understand it, not yet a selective state space model, but just a traditional state space structure combined with the attention mechanism. And it is a globally competitive 7 billion parameter model that you can already get access to through the Together AI API. So that happened quickly, and we can assume that the selective state space one may soon be coming as well. There is also another paper recently called Block State Transformer, and this one even gets more into the weeds. It is a deeper integration of state space and attention mechanisms. It is, again, not yet with the selective state space model, but a global state that can get fed into an attention mechanism. So in this block state transformer unit, they now have still the self-attention of text to itself. Then they also have a cross-attention of the text to the context that is evolving through time. And this is, again, very competitive. I won't get into the details on this one as much, but suffice it to say, it's doing its fair share of winning. And again, this is without even having the selective state space model. The selective state space model was just published 2 weeks ago. The block state transformer came just a little bit after that. The Striped Hyena came just a few days after that as well. They've already announced that they're at least taking the architecture now up to 600 billion tokens of training. Again, with the recurrence there, it seems like it's not as easy to parallelize as other things, but they're going to continue to push that, I'm sure. And there's just so much room for remixing that I think we're nowhere near done. We've gone from one core building block to two, and we've only begun to think about how we might remix them. I think we're also going to see probably a lot of evolution just of the state space model itself, right? The transformer has gotten all the attention because it was working. The transformer has been optimized like crazy because it is working. The state space models didn't attract that kind of attention because they weren't really broadly competitive. But now that we've seen this demonstration that they can be, how about moving from, say, a single state to a multi-state model? We see this already with attention, right? There's not just one attention head, there's multi-headed attention. And I think you can certainly see an analogy where multiple states might make a lot of sense. You might have different states which are responsible for different things. One great unlock that the state provides is it's another thing that you can make a target for an optimization process. So what I mean by that is with the transformer, and as far as I can tell, so far also with even this most advanced selective state space model, all of the optimization is just on the language prediction. We're just talking about pre-training perplexity measure. It's just how well is the model able to predict the next token in whatever text it happens to be being trained on at the time. But with the state space models, you also get out a state. And that state can have various properties. And you might even think about optimizing multiple things. You want to optimize the prediction, but you might also want to optimize some properties of a state or multiple different states. One really natural way to do this would be to have some sort of contrastive objective between the different states, just to push them in different directions, right? We might have multiple states. We might want to optimize all the states when it comes to making a good prediction, but we also might want to try to create an incentive within the training regime to make the states look different, a richer and more robust overall representation, perhaps. You might also have some states that are dedicated to specific purposes. I think one of the really interesting things is going to be, to what degree do people take another conceptual elaboration here? You might imagine, for example, a built-in classifier. Again, in the transformer, you have this forward pass layer by layer. You get a prediction out. That's all you get out. And we can try to go into the middle layers and use techniques like representation engineering or whatever to see, based on the activations, does this appear to have a certain concept loaded in and active or not? That's starting to work, but it's definitely kind of messy. You can also have like classifiers that sit outside and try to filter inputs or try to filter outputs or identify when things are problematic. But you don't really have classifiers built in. You try to do that with RLHF and you have a hell of a time doing it. Lots of false positives, lots of false negatives. You could imagine, though, having multiple states within a state-space model where, again, they're all working together perhaps to make a good prediction, but maybe one of the states is specifically optimized as a classifier such that they may fire off in a different way as well, in a way that can be aware of the full history, that can have all these beneficial long-term memory properties of the state-space models. But because the state is also something that you can optimize, you might be able to turn different states into effective classifiers. So maybe you're getting both an output in terms of the next token, but also getting classifier values out at the same time as well. Very interesting potential, I think, for things like that. You may also see different kind of wirings. Maybe you feel like this long-term memory is great, but I can't necessarily fully trust it. Maybe I need to look at the current state, but also some historical states. I can't save every state because keeping in mind the only reason this is scalable in the first place is that the traffic from the high bandwidth memory to the SRAM that is closest to the cores has been designed in such a way that the traffic there is minimized. We can't just take every internal state and remove it and save it, but we could do some. We could accept some performance hit to have some historical states. And maybe we would find that if we have my last state, but also some selection of historical states to work from as the current input, perhaps that could work even better. There could be hierarchies of states. There could be mixtures of experts built into this kind of architecture as well. There is a whole host of opportunity for innovation and elaboration, I think, in this new architecture, just in the same way that there was with transformers, but again, even more so, because now we have two fundamental building blocks that seem to work comparably well and have these different strengths and weaknesses. What other kind of things might we see? New wiring diagrams, new ways to branch, perhaps some way to recover the parallel form for training, perhaps through an approximation. It does seem like fundamentally this selective mechanism is by definition recurrent. But if we were to accept some imprecision, could we create a convolutional version that would be close enough to load in a bunch of context to get something off the ground fast or to facilitate training? I would not be surprised if something like that is possible. We might see regularization techniques that are really interesting with memory. Just thinking about the human cognitive experience. We can remember what we had for breakfast this morning, many of us, most of the time. We can remember maybe the best breakfast we've ever had, and we can remember what we normally have for breakfast. But we certainly can't remember every breakfast we've ever had. So there's some sort of abstraction happening, some sort of compression happening where things that are not outliers that fit patterns, we get rid of the details of those individual episodes of our memory and we compress them into the general memory of what I typically eat for breakfast, as opposed to a bunch of super specific individual breakfasts. So I think you're probably likely to see some sort of weight decay. You might call it state decay. Weight decay, you basically say by default throughout the training process, all the weights are going to get lower. They're going to get smaller every step. And then the only way that they're not going to get smaller is if they specifically get turned up through optimization. This has been shown to be pretty key to the grokking phenomenon, where the generalization that happens seems to depend on the fact that the model's first solution, which is just to memorize, gets gradually weaker due to the weight decay, but the actual algorithm that solves the problem continually gets turned up and overcomes weight decay. And when that gets turned up enough that it is the dominant mode, then you have the grokking. Some version of this also certainly happening in the human memory, where clearly a lot of details are pruned from our memories. There's work there to be done, but my term there is state decay, from weight decay to state decay. Not to say we won't have weight decay as well in these state-space models, but state decay is something that, has just been there for a while that doesn't appear to be useful. Can we just gradually let go of that stuff and maybe have multiple states so that they do it in different ways, where some try to retain and others try to let go, so that we have a robust multi-state representation that maybe can do a little bit more than any individual state with a single training objective could do on its own. Finally, before moving on from the architecture bit, here's a quote from the Together AI blog post about the striped hyena model. They say, early in our scaling experiments, we noticed a consistent trend. Given a compute budget, architectures built out of mixtures of different key layers always outperform homogeneous architectures. This was a conclusion that I came to in my own reading and just thinking about this. And then eventually I came across this quote. So I don't want you to think that like I'm taking too much from this one quote. On the contrary, I thought it was like a perfect representation of what I had inferred was likely to be the case. So we're headed for a future here where we're not going to see the same attention block is every single layer. We're also not going to see that the selective state space block is the only thing that matters. Instead, we're going to see that these architectures built out of mixtures of different key layers are going to be the way, and that they'll probably blend together. And that's what the block state transformer is all about as well. So what else can we begin to expect if all this analysis is right? On the hardware dimension, the state itself is another dimension for scaling. We have the parameters. That's been the main way that we've talked about models and their scale. And we also have the context window, which we've been scaling in the transformer. But here we have something new. We have this state, which is itself of finite size. And it is where the information from the current episode, from the current context, has been compressed. So how big that state can be is a pretty important question. You are fundamentally limited by the size of the state, how much information you can actually bring forward. So I think this doesn't seem to be explored at all in this current paper, but how big the state is definitely something that you will want to push, right? And I would expect that just like we saw a rush for bigger parameter counts and longer context windows, bigger states is something that is going to ultimately get scaled. Is the current hardware optimized for that? Probably not. If you just consider the fact that the algorithm here was developed in a hardware-aware way, that sort of implies that the hardware was not designed for this algorithm. Well, we've certainly seen hardware designed for transformers. It will certainly take a while if we are going to see hardware designed for state space models, but I wouldn't be shocked to see something like that happen. I'm not exactly sure what that would look like, but perhaps it would look like a different ratio between the SRAM or the shared memory and the high bandwidth memory. Right now, from what I've seen over the last couple of generations, V100, A100, H100, those memory sizes are roughly growing at the same pace. Whatever has determined that ratio, the ratio hasn't really changed over the last couple of generations. If I'm right about all this, we may see higher ratios of shared memory to high bandwidth memory, because maybe the models don't necessarily need to get all that much bigger, but the states need to get bigger. And so the hardware may have to adjust to allow for that. Beyond that, how much more can we get out of SRAM and into some longer term storage? It's kind of crazy, right? The state is the important thing here, or at least it's the big new innovation that gives us this possibility of longer term memory, more coherent, in all likelihood, more agentic sort of behavior. And yet the state itself doesn't exist anywhere except in this very small amount of the highest speed memory. And by default, it's not exported from that. So it's not saved anywhere. So all the states by default are lost. If we were to try to get all the states, literally every timestamp, off of the SRAM, then it would probably be prohibitively slow. But how much more might we be able to sneak off the SRAM? Or could a different chip have a somewhat different design where information could flow out of the SRAM into some sort of storage without clogging the critical input channel? I don't know, but it does seem like a question is going to be, what more can we get out of SRAM and at what performance cost? And eventually, is there any hardware modification that could ease that? Because I do think we're going to want to look at historical states for sure. And just to get one historical state off, that shouldn't be too big of a problem. But to get like lots, to get every 10 states or every 100 states or every 1,000, that's going to be a lot more, especially if you're talking millions of steps in an inference. If you want it every 1,000, you're looking at 1,000 states. How much does that slow things down? I don't know today, but I think that's another area where There's going to be some interesting scaling laws and analysis on current hardware. How much can we save out of these internal states without tanking performance? I really do think that's likely to matter. Then you might think about application development. So let's imagine these things start to realize the potential that I'm talking about. And we start to have models that whatever exactly their internal wiring, they have this long-term memory, that they start to have something that the transformers lack, that they have the ability to evolve meaningfully over time, that they can, because they have this longer-term coherence, that they can start to be more predictable in their behavior, fundamentally less stochastic, fundamentally more shaped by all interactions that they've had, something that can evolve with you, something that can really, in a much deeper, longer-term, holistic way, actually start to get to know you. And again, all that's going to take a lot of work, right? The data part, I think in particular, we have to go create the data that incentivizes that. And that doesn't really exist much today. I would not be surprised if we start to see it come online relatively quickly, but it doesn't exist yet today. So we are going to have to go and create that. But as that starts to come online, then what sort of things are going to be possible in terms of applications? I think one thing is we'll see a shift probably from context management to something that you might call context selection. Or another way to say that is maybe you go from RAG to something more like state search. So what do I mean by that? It's like really long contexts, you aren't going to want to have to recompute every time, right? If you're looking at reading a whole body of literature in order to load up the latest and greatest knowledge into the context, or if you're talking about reading somebody's whole email history to really get a sense for who they are, you're not going to want to have to redo that for every single inference. It's not going to be practical. So we're going to have some states which get arrived at, exported off the SRAM at whatever performance cost. Again, it'll definitely be acceptable to do this from time to time to cache a state. Just how many you can do will be interesting to find out, but you can definitely do one here or there. So if you want to run through a million or millions of tokens and build up this state that has evolved through that entire history, you definitely will be able to take that state and save it. And then you might have a lot of those running around. So instead of having to be very careful about what specific text do I put into context, maybe the idea is more that we have a big library of pre-computed contexts, which we can then select from. Today, I'll often give a few shot example, but maybe in the future, I can go to a library of existing contexts that have done hundreds or thousands or a million of those problems, right? Or read the whole textbook and then did 1,000 problems and are now ready to solve my particular problem. It seems like that is going to be a potentially big deal. And again, going through a database and retrieving some text and putting that into the prompt, that feels kind of clunky by comparison to saying, do I have any states that have what I need? This also suggests, why would you want multi-state architectures? Well, maybe you want one state that's kind of your core state, but then you want auxiliary states that have information. Again, we sort of work this way, right? I'm Nathan, I'm me, I'm like going through my day, I know what's going on. And then I get into a mode where I have all this working knowledge that's really front and center in my mind. And then I might go switch to a totally different context and go play with my kids. And I have kind of a different, seemingly quite disjoint set of mental states that are associated with those two things. But in some sense, I'm still me, right? I'm not suggesting that I work like these state space models work or that they are going to work like I work, but I just see that behaviorally, I have this kind of flexibility, and I can imagine an architecture now with, again, perhaps a core state or a couple of core states, and then swappable states. Another way that I've been saying this is from mixture of experts to mixture of states. Can we take these states and recombine them in interesting ways? Almost for sure. It seems like that's almost for sure possible, right? We see that in representation engineering, even within the transformer mid-layer activations. It seems almost for sure that you would be able to take states and combine them, perhaps with weird, unexpected consequences in some instances, but functionally, almost for sure, that should work. There's also disposable paths or self-delegation could potentially get a lot more interesting. I was trying to use an agent platform the other day, and the agents still don't quite work. So I'm trying to use this agent platform to do something, and it involves searching through my email. My email has a ton of stuff in it. The search returned a ton of things. And then it kind of broke. It was too much, couldn't page through it effectively or whatever. And I was looking at it and I was like, I can see why this is a pretty big challenge. Because even if you're using GPT-4 Turbo or Claude 2.1 and you've got north of 100,000 tokens, like an email search out of my email, I need to delete more stuff. But man, a lot of people have a lot of email, right? We have gigabytes of email. So the search results go pretty deep. And then you need to scan through them and figure out what's relevant. And you can self-delegate that, but the transformers just don't handle it super well. Whereas you might imagine a state space model scanning through these long search results much more effectively. And this is actually an area where you could also imagine the state space model parallelizing really well. You might say, okay, I've come as far as I've come. I'm at this state. And now it is the time to search through the email. Well, maybe I can just take 20 of myself and divide that work 20 different ways and each go through a page. And for each email, I'll be asking, does this seem relevant? And if so, I'll indicate as much. And then that way I can really quickly scan through all the stuff with a ton of context to determine what's relevant and not relevant. Then once I find all the stuff that's relevant, then I bop up a level in my recursion depth. And now I can just discard all those versions of me. And me here is the selective state hybrid architecture of the future. We can just discard all those versions that actually ran through all the annoying, irrelevant email results. And we can just pop up and say, okay, here's all the relevant stuff. Maybe you have some notation that like we performed a search or whatever, but you don't need all that. You don't need to recall. You don't need to clog up your context. You don't need to clog up your state with all the random emails that were not relevant, right? So instead you just run that process, discard, and then pick up back where you left off with all the stuff that actually is relevant. I think we are likely to see far more agentic behavior and far more robustness, far more apparent sense of direction or purpose or kind of unity toward goals based on the fact that we can build up these really long contexts. You might even think of things like developing sort of a immune system, a runtime immune system as a state, right? This gets a little bit beyond what we typically think of as the cognitive, but the human immune system has memory. It knows what it has seen in the past. Sometimes these memories fade, other times they last a lifetime. Obviously, it's all super complicated, but the human immune system is, in a very fundamental way, built on a memory system. So what would the equivalent of that be in one of these state space models? What if it was just a log of all the attacks that are known, right? We maybe can't train into the core weights that there's all these attacks. Who knows what the training mix is going to look like? Fine tuning in general has not proven, at least for transformers, to be a great way to teach facts. So new kinds of attacks, new things to watch out for. Those are tough, right? OpenAI has their system prompt, and there's a lot of debate that happens around when they get embarrassed by some failure of ChatGPT, and then later people report it being fixed. People accuse OpenAI of changing the system prompt. At this point, it's pretty well established that they're not changing the model that frequently, but they can change the system prompt. And so maybe they can just go in there and be like, hey, watch out for this, and have it watch out for that. And hopefully the storm will blow over and we can include it in the next data set, but we can at least catch the behavior and stop the embarrassment for the moment. I don't know how much they do of that. I suspect not all that much, because clogging up your system prompt with that kind of crap just doesn't seem like the kind of trade-off that they would want to make unless it's a pretty serious vulnerability. The fact that my spearfishing thing like always worked, they could have easily said like, do not spearfish in the system prompt, and that probably would have stopped it from working, or at least would have helped quite a bit. So I don't think they're doing a ton of that. But with the state space paradigm, you can imagine doing a lot of it. You can imagine a dedicated state within a multi-state model. You can imagine keeping much more up to date on recent reports. These are the things that you really need to be watching out for now. And potentially those things could be passed around in a far more lightweight and rapid way. And if it is a dedicated state within a multi-state model, you potentially could get significant robustness out of that. I mean, that's how we do it, right? The old shame on you for fooling me once, but shame on me if you fool me twice. You know, that's because I have memory, right? I'm supposed to remember it, and I'm supposed to recognize it, and I'm supposed to know better the next time. And the transformer just doesn't have that mechanism. But the state space models definitely do. And the question is, can we shape it, and can we get the performance to where we need it to be, to where we can really trust it? I strongly suspect we can. I strongly suspect we are going to see much more agentic, much more goal directed, much more consistent, much more predictable behavior, much less weird going off the rails, less apparent stochastic randomness. And I think all of that is probably going to be unlocked with mostly data sets. If I had to guess, I would say it's like 2/3 data sets and 1/3 architectures. You're going to have the data sets to train into the various architectures, and the architectures will co-evolve. If you're thinking about data sets and you want to build one, by the way, I would really emphasize, this would be true at any company as well. I've said before many times, AIs can handle tasks really well, but jobs are too big for them. If this changes that, then the way it's probably going to happen is that people are really going to start to record jobs. Instead of just having these more manageable bite-sized units of tasks, we're going to have to start thinking about data sets and super long episodes as ways to record jobs. And I think it's also going to be really important, to the degree that we want to automate whole jobs and we want to do that in kind of a robust way. It's going to be important to make reasoning explicit and to really capture reasoning. This is important already on transformers. I've covered a few different times how when I tried to fine-tune GPT 3.5 for the Waymark script writing task, it didn't really work. At first, it didn't seem better, maybe even a little worse. And then when we started using reasoning steps in the data set to make clear, this is how we want you to think about it. First go through the reasoning, the strategy, and then write the script. Teaching it, this is how we want you to approach it, and we want you to spell it out and then do it, dramatically improves performance. I think that there is this kind of analogous reasoning or identity or narrative level that people have that seem to guide our actions over time and make us legible and predictable to one another and help us stay on task, that probably gets built in here too. It's not just about, this is the task, this is how I break it down, this is how I approach it. But if you were really thinking, how can I get an AI to do a job? One of the things I think is missing, that you don't really find this on the internet, right? It's the higher level narrative of, who am I? What is my job? What are my goals? What am I doing right now that's in pursuit of that, right? That's all always somewhat in mind. And then it can fade a little bit as you're really getting into the task. But you select your task. You decide what to do based on this stuff, right? And you decide when it's worth pushing through difficulty versus when it's worth giving up and going and doing something else instead. These decisions are guided by this high-level narrative. And we don't really have that in the training data. It's not on the web. So I think we're really going to have to work hard to capture it. And it probably just starts off by having people monologue more and just force people to take the moment to really spell out, who are you? What is your job? What are you doing? And to weave that in to all the activity. I think that is likely to be a big part of how we can get the AIs to imitate human behavior. And again, that data doesn't really exist yet, certainly not at the scale that it's going to need to exist if we're really going to see the sort of performance that I'm expecting from all this new technology. Okay, what about interpretability and safety? This is a really interesting topic, and I've seen different takes on it. One simple take, which I think definitely has something to be said for it, is maybe this is a huge win for safety work and mechanistic interpretability work because the state itself is such an obvious thing to focus on. It's like, wow, with the transformer, we have all these internal activations and circuits, but what's happening? It's also alien. Here, because we have this state that is the long-lived state, and you kind of compare the last state to the current state and to the next state, it does seem like that is a very natural object of study. And to look at what concepts are activated, to look at concepts like intent. Is there deceptive intent? Is there helpful intent? Is there harmful intent? It would seem that you can really zero in on this particular thing and study it super intensively. Techniques like representation engineering that I've mentioned a couple times are seemingly likely to be pretty adaptable to this. Circuit type approaches perhaps as well. You have a ton of weights still, right? You still have billions of parameters that are involved in this information processing. So studying the circuits that develop within those, that's definitely also a thing. But the existence of the state as something to focus on does seem like it could be a huge advantage for interpretability and safety. At the same time, at least as it's currently set up, the fact that the states are never actually taken off the SRAM at all, and you don't have access to them, and that's somewhat necessary for performance reasons, does suggest that you can study these states. But if you actually want to monitor states at runtime, right now we don't have a great way to do that. If you're tinkering and you're studying, you're doing interpretability work, then yes, you have a natural place to focus your energy. But there's not a practical way to say, in fact, it would kind of violate the whole premise of the hardware-aware algorithm to say, I want to export every state so I can study it later. You maybe could fit in some sort of checks that could happen purely on the SRAM, and that could be another output. But definitely some innovation would have to happen there to have a state-of-the-art state monitoring applied at runtime without a major performance hit. Again, maybe we see hardware changes there where there's more SRAM and it makes it easier to do, but very hard to say right now. Just behaviorally, I would guess there will be as many surprises and weirdnesses with these as there are with transformers. Maybe with the hybrid mechanisms, you start to get somewhat less behavioral weirdness because they hopefully get the best of the strengths and the weaknesses are compensated for. But if I were just thinking pure state-space models, I would expect a lot of weirdness. And even with the hybrids, certainly should be open-minded to behavioral weirdness. And so I do think we're set back a bit in terms of just understanding AIs generally. Like, what can they do? What can't they do? What do they trip over? We have answered that to a decent degree for transformers, but we have not even really begun to answer it for state-space models. We can only begin to answer it now. Zooming out, bigger picture still yet, considering philosophical questions and questions of human AI interaction dynamics. I think if everything I said about the agent capabilities is true, if because of these long contacts, we can start to see more coherent, consistent, predictable, legible behavior, if these things can evolve over time and get to know us in some sort of more intuitive, deeper way, then I think we're going to have a totally different relationship with them. It's going to be much easier to project value onto them. We already see this happening, of course. Go back to our second episode with Replica, people falling in love with like pretty primitive chatbots. Now we are seeing character AI. People are spending hours a day. All sorts of new sex bot chat app type things are coming at us. All of these things still don't have long-term memory. We still don't have a mutual evolution with them. This could really change that. And if it does, we are going to be much more inclined to see these things as real value, right? And the loss of a state with all the context that it represents could be like a real loss. You may not even be able to recreate it, right? Because again, that log is not there by default. You could log every input, but by default, most people are not going to be logging every input. And intermediate states are lost. So losing a prized state or a valued state, that could be a real loss. Not the kind of thing that's easy to get back. Not like with a transformer, you just reprompt or whatever. It might not be like that anymore. These things might have more durability. And they might even merit more moral weight, right? I don't really know why I'm conscious. I certainly don't claim to have the mystery of consciousness solved, but I hope to do an episode on this. One paradigm for understanding consciousness relates to just the fact that we can have this kind of long time horizon awareness, and that to some extent that comes about by us modeling ourselves. We definitely have an ability to predict how we're going to feel in the future. We may be right or wrong, but we do have a kind of running prediction that helps us when things are changing from our expectations. We realize that in part because we do have this, at least a little bit ahead, planning for what am I likely to be experiencing next. When that expectation is violated, it definitely brings things to our attention. You can definitely imagine these state-space models self-modeling, right? What if you had a dedicated state whose job it is to model what the likely state is going to be 50 states from now? That's a bit of a trick to pull off, but it does seem like there's nothing fundamentally blocking that. And that's getting close to at least one definition of consciousness. Will there be subjective experience? I have no idea, but it's much easier for me to imagine caring about an AI that is powered by a state-space model with a long-running, super high context state, and to be right about caring about it as compared to caring about a character that's coming out of a transformer model today. I'm radically agnostic about these things, but certainly it seems like this is a significant step in that direction. If you've ever heard of The Age of M by Robin Hanson, I would say a classic that is more classic now as a result of this. He postulates a AI that essentially simulates a human brain or emulates a human brain. That's why he calls them M's. And they're supposed to be very human-like because they're to a high enough degree of precision emulating what a human brain would do. But they have all these different properties because they are digital. They can be paused and put into long-term storage and then woken up. And when they're woken up, time has passed, but their state isn't changed because we have this durable digital storage. And so he envisions a world where that plays out and these things are easy to clone, right? You can spin up a bunch. I alluded to that in terms of application design and in terms of self-delegation to go scan through a ton of emails. A lot of the analysis in the Age of M is way more apt in a future where long-running states are a key component of what AIs are. We're not headed immediately for real high-fidelity emulations, but we may be headed for enough of the core capabilities such that a lot of that analysis is going to, I think, start to become more and more relevant. You look at the transformer and you look at the M's and you're like, these are just so different that I don't really think the analysis of the M's and like how that's likely to play out in terms of economics, society, whatever, I don't think that follows from transformers, but much more so. It seems like it could follow from the state-space architectures. So hopefully maybe we can get Robin on to go through that because I think it's only looking more and more relevant. Now, okay, zooming out again a little bit further, just kind of talking big picture. If you are looking for investments to make, if you are looking for companies to watch, I would definitely look at both of the companies that the two authors of the Mamba paper are affiliated with. That's Albert Gu. He's the chief scientist at Cartesia, and Tri Dao. He's the chief scientist at Together AI. Cartesia specifically says that they are training models with sub-quadratic scaling properties, and this certainly fits that bill. Together AI seems to be even more focused on just, as you'd expect from Tri Dao's hardware-aware, super close to the metal programming. They seem to focus on infrastructure, managing compute, getting the most out of compute, et cetera, et cetera. Given that both of these guys are involved with startups, it is a little curious that they published this research. We are in a moment of general closing, and I would be fascinated to talk to them about why they chose to publish this work. I think this is the kind of thing you could keep secret, especially given how it's not just a high-level conceptual thing, but it's also the low-level implementation details that are so important to making the thing work. That's the kind of thing you can keep secret. Right? You can keep CUDA code in a highly specific implementation. That you could keep secret. So they chose not to. It's out there. Maybe they even have more secrets that haven't been shared with the public. But this is a pretty big paper and the code base that I am kind of surprised is published in today's day and age. Just as a thought experiment, if they had taken it to Microsoft and tried to sell it, I would expect that they would have been able to get a lot of money for it, but they didn't. So it's out there. Unless I'm way wrong about what this can enable, that definitely just means acceleration will continue. OpenAI is well known for pouncing on stuff like this. When I've shopped this idea around to different people and said, what do you think? Why might this not be as transformative as it seems like it would be to me? And one of the interesting speculations I got back was, well, maybe the leading labs already have something like this. And so therefore it's baked in already to the very best stuff that we're seeing. Maybe GPT-4 has an element of this. I don't think that's true. Certainly the way that they are presented seems to be like, you have a context window, you can't go past it. So I don't see anything to suggest yet that there is something like this. The leaders like OpenAI, they didn't invent the transformer either, obviously. What they have done is they have pounced on the advances. They have really tried to push the performance and maximize it. They've really tried to figure out what is this good for. They are obviously highly invested in data creation and collection of all sorts. They're doing licensing deals now with all sorts of different data providers. I would guess that they already have somebody internally, maybe even a team, working on characterizing this. I would guess Anthropic is probably already doing the same. If it is working, they will make it work. And interestingly, with OpenAI in particular, Their new assistance API would be dramatically improved with an architecture like this. The assistance API, which is basically the GPT's API version, allows you to have arbitrary length threads and also documents, RAG style knowledge base that's attached. But this arbitrary length thread, you think, well, how do you have an arbitrary length thread if you have a finite attention window? The answer that we've got so far is that the assistant basically queries its own history as part of your, subsequent call and fetches history that's relevant and loads that into context. And then you are charged for, and this has not been totally clarified yet, you are charged for the new inputs and outputs, but also whatever was fetched out of history. That's a little bit messy. It doesn't sound that awesome. It would be totally smooth with an architecture like this, right? You have now an arbitrary length. You have that history. Yeah, you can query it perhaps if you need to, but you have this state that is propagating through time. And this would also lend itself to, again, if used in pure form, and I don't think it's going to be pure form, I think there's going to be hybrid with attention, but if used in kind of pure form, then you could also imagine, hey, you only get billed for the additional inputs and outputs at any given extension of the thread. That could be a huge deal. So I think OpenAI is advantaged by this probably relative to other things, which is, again, why it is kind of confusing as to why it was published. Their ability to pounce on things, to drive scale, to really get relentless on the question of what is going to make this product work well is going to be a huge advantage here, because this is something that is just new and totally uncharacterized. And I do think their assistance API, if there was anything that broadly, I think they don't have this in their production stack yet, but they might have something like it in the pipeline. And if I had to cite one piece of evidence that would make me think, yeah, maybe they do, it would be the nature, just the structure of the assistance API. The assistance API looks like something that was built a little bit more with this kind of architecture in mind, honestly, than with the transformer. Maybe you could think of it as like a bridge from a pure transformer structure to a future structure that they anticipate. Time will tell. Agents, we're behind. I've been thinking a little bit about coming to the end of the year. What have I been right on? What have I been wrong on? I definitely expected more progress on agents than we've got. One of the big reasons I think that we haven't got as much as I expected is that GPT-4V has only recently come available. It was demoed in March. We had expected to see at that time that it would be launched soon and that multimodal inputs would quickly become the norm. And I definitely think that vision is super important for effectively navigating even just the digital world, right? Even just doing stuff in a browser. The browser is meant to be interpreted visually. And only recently has that really become possible. So now we have the application development agent work to be done on top of that. I think there is a big unlock there. And I think we're going to get to effective agents regardless, even if we do have to brute force it through purely transformers, between the vision, between doing things like rewarding reasoning. OpenAI had a result earlier this year where they achieved a state-of-the-art on the math benchmark by giving a reward signal at every intermediate step of reasoning as opposed to just the final result. I think that is going to work for agents. If I had to guess like what GPT 4.5 would look like, if you interpret the TikTok of the last generation, if GPT-3 was a certain scale, a certain kind of latent power, and then 3.5 was when they really applied the RLHF and made it behave, then GPT-4 is another bigger level of power. But it was released before this paper came about the rewarding intermediate reasoning. And so maybe GPT 4.5 is still the same raw power, but just like way more reliable reasoning. That's kind of what I expect from GPT 4.5. Context windows continue to go up as well. We've also got new scaffolding. Obviously, we've got RAG, but we've also got skill libraries. There's a lot of reasons to think that agents will work. But this seems like a qualitatively different reason to think that agents will work. That with the long-term memory, with the big enough states, with perhaps multiple states, it seems like there is a path to a level of coherence, robustness, legibility, predictability that will make these agents both far more effective and also just far more familiar in the way that they proceed. And finally, I think all of this does suggest that things are getting a bit out of control. You've heard me say that, that things are perhaps out of control many times. I would like to emphasize that I think right now we are hitting a moment where there may be a qualitative shift in just how out of control things are getting. A totally different line of research, but just again in the last week or two, DeepMind put out a paper in Nature about a technique called FunSearch, searching the function space, where they used a frozen language model. That means, again, the language model weights are not changing. They're not even fine-tuning it. But nevertheless, they were able to use it to advance the state of the art in a number of problems, including a couple of mathematical problems that have been open for decades. This is pretty remarkable. The way that they do it, they have to have things where the solution is scorable. This relates to the PNP problem division, where certain kinds of problems are very hard to find the answer to, but are very easy to verify the answer to. A classic example of that would be factoring the product of two large prime numbers. If I give you some giant number, and even if I tell you like, hey, this is the product of two large primes, you're going to be at it for a while before you can figure out what those primes are. Cryptography is largely based on the extreme challenge of this problem. However, if you have the private key, if you have one of the prime numbers that was used, then you can just do the division and there it is. So it's very time consuming to find the answer, but it's very easy to verify the answer. This DeepMind paper is for problems like that. This almost bears its own episode, but the way that they do it is they use the language model, they generate ideas, they give it like its best recent attempts, functions that have scored the highest, and say, here's a function, here's how it scored, here's another function, here's how it scored. Your job is to come up with a new function that will score even better. And it took a lot of generations, but not that many. I think they reported 1 million generations in this paper. But 1 million generations, we're talking low tens of thousands of dollars at retail API price with GPT-4 pricing to run 1 million generations. So not that much. And with a little bit of additional clever structure to make sure that they were trying novel strategies and whatever, and the fact that they could quickly score the results, they're able to advance the state of the art on multiple open math problems that, again, people have been working on and have been open for decades. That paradigm seems to extend extremely naturally to exploring the architectural space in machine learning. And particularly now that we have not one, but two different fundamental blocks that are like equally expressive and have these likely quite complementary strengths and weaknesses, where the attention is really good at dense analysis and every token relates to every token and we can see everything that's under consideration clearly in one view, versus the state space where you have this long-term memory and the ability to learn from lots of examples, but also have to let go of certain information over time. This architectural space is barely explored at all. And AI could probably do it. GPT 4.5, even 4, right? I mean, this was Cody that they used, which was a Palm 2 generation fine-tuning on this DeepMind paper. So that's not even as good as GPT-4. But you take GPT-4, you apply a similar structure, you say, here are the two blocks that you can really play with that are like your fundamental units. You can reorder them, you can remix them, you can have different sizes at different layers, you can have different interleaving patterns, you can have different kinds of skip connections, you could potentially even define new ways that kind of bleed the blocks together. And each time you do that, we will actually do some training. We'll actually instantiate that model. We'll run it through some training and we'll compare it to other models that were trained on exactly the same initial data. That can be pretty fast. In previous episodes, we've done analysis of like, how big does your cluster have to be to train GPT-4 in how many days or whatever? Well, the biggest model, the 3 billion parameter model, is still like 5 orders of magnitude less compute than GPT-4. And you don't even need that. Maybe you can get by with 1/1,000,000th. Maybe you can even do 7 orders of magnitude less. If you see something that, hey, in early training, it's beating things that are currently our best, then those are the things that you want to look at, right? So to take a language model and have it do a million different versions, now the score is not so easy to calculate for each of those million. If each test takes 1/1,000,000th of GPT-4 compute to evaluate, then when you do a million, then you've basically consumed all of GPT-4 compute. So this would be a big undertaking still for a significant lab with significant compute resources. But might you expect that GPT-4 with a million attempts could beat the state of the art? I would bet it could. And what about the possibility also that as the state of the art improves, it's not GPT-4 doing it, but it is in fact some state, space, attention hybrid doing it? I'm assuming that one of the biggest challenges in the DeepMind paper is that, hey, we need to avoid the same generations over and over again, right? Like if you have the language model do the same task a million times, you're going to have to take care to get it to vary what it's doing. But if it has a long-term memory of its own, then perhaps it can be incentivized to explore different kinds of spaces within the architectural space without having to be tortured so much into doing it. And again, you need the training data to create that kind of behavior if that's indeed the kind of behavior that you want to create. But it certainly seems far more possible than it ever has before that highly agentic, highly goal-oriented, highly on-task, little specialized agents might soon be doing the machine learning architecture, R&D, or at least a significant share of it for us in an automated way. And if that is beginning to happen, then we're really starting to close some fundamental feedback loops that begin to look like some sort of takeoff, some sort of intelligence explosion. So with the big caveat that maybe I have this all wrong. Maybe it's just not going to work. Maybe it just won't scale past the 300 billion. I don't know why that would be. The scaling laws so far have been pretty predictive. But yeah, maybe I have it wrong. Maybe it just won't work. But if I'm right, I think we are looking at not the end of Transformers, but the end of the Transformers era. The end of the time when the same exact block repeated over and over again would give you the very best performance. And instead, we would be heading into the beginning of a new multi-architecture era where we will likely have even faster recombining of these elements to create ever better and also ever more specialized architectures, where we will have proliferation and evolution so quick that it's going to become increasingly hard to analyze and make sense of. This is already pretty hard. I've spent the last 2 weeks trying to understand this from every angle and try to figure out what's going on. There's a lot more to come. I think it's going to be very hard to keep up with this stuff, particularly if we start to see the loop close where the models can do the exploration of architectural space to build even better models. I think we're going to see all that and more effective agents, more compelling long-term assistance, more compelling long-term AI friends and companions. All of this, if I had to guess, I would say it probably happens several times as fast as the Transformer era has already unfolded, right? From 2017 here to late 2023, a 6-year period of Transformers invented to today. I would say this new architecture gets validated, assuming it does, and gets elaborated in a similar way in probably a third or maybe a quarter of the time, in part because so many more people have piled into the space, because the hardware has ramped up, because the data sets are there, because the benchmarks are there, because the models are increasingly able to help. All of these factors feeding into the same dynamic. The cycle is turning tighter and tighter. So if you thought that the cognitive revolution was going to give you any rest, I am sad to say that I don't think that is the case. If anything, it just seems like the intensity is turning up and up and up. The cycle time is getting shorter and shorter. And all I can say is buckle up. It is both energizing and enlightening to hear why people listen and learn what they value about the show. So please, don't hesitate to reach out via email at tcr@turpentine.co, or you can DM me on the social media platform of your choice.
OmniKey uses generative AI to enable you to launch hundreds of thousands of ad iterations that actually work, customized across all platforms with a click of a button. I believe in OmniKey so much that I invested in it, and I recommend you use it too. Use CogRev to get a 10% discount.